Ma, and he will talk about simulations and metallicity gradients.
My name is Xiangcheng Ma. I'm a grad student at Caltech, working with Phil Hopkins in using the fire simulations. Yeah, it's on. First, let me introduce why we care about metallicities in galaxies. Not only we can understand the formation history of galaxies using chemical evolution of galaxies, we can also understand and test feedback models in the galaxy, theory. Here's a plot in one of my papers in 2016 studying the galaxy mass metallicity relation. We compare different hydrodynamic simulations and semi-analytic models that predict the mass metallicity relation across redshift from redshift 0 to redshift 3. You can see all the models' predictions are all over the place. So the metallicity is very powerful in testing the feedback models. So why metallicity gradients? We understand for decades that local galaxies have negative gas phase metallicity gradients. In this talk, I will focus mostly on gas phase metallicity gradients, which means the metallicity of gas is higher in the center of the galaxy than at the outer edge of the galaxy. It's very straightforward to understand the negative metallicity gradient, starting from a pure gas disk with a power law profile. And we know the star formation follows the Ks law, which is the 1.4 power of the gas surface density. Then if we assume local closed box approximation, which means no metal mixing between annuli, then the gas phase metallicity is proportional to the mass fraction of stars, which goes to r to the minus 0.4 times the original power law index. So it's produced a natural negative metallicity gradient. But what we know at high redshift, since 2010, there are individual observations using lensing galaxy plus FU technique plus adaptive optics. Observations of lens galaxy at higher redshifts basically produce a few samples produce very steep metallicity gradient. So if we plot the metallicity gradient versus redshift for a few samples available at that time, we can see the high redshift galaxies actually have very steep metallicity gradient than the galaxies at lower redshift, which suggests this might be just the traditional inside-out growth, which means the galaxy form a very compact core at high redshift, which have a very steep negative metallicity gradient. Then as galaxy evolves, the galaxy size grow, and the metallicity gradient flattens at later time. But recent observations with enlarged sample of lensing galaxies at higher redshifts shows pretty all over the place. The recent observations show very diverse distribution of metallicity gradient in high redshift galaxies. There is some theoretical work using hydrodynamic simulations that shows, so if you have very weak feedback in the simulations, you tend to have this inside-out growth picture, which the metallicity gradient is very steep at higher redshift and then evolves to flatten metallicity gradient. But if you have stronger feedback model in the same simulation, you kind of get a flat metallicity gradient from high redshift to low redshift. But why there's a diverse distribution is not answered in this simulation. So to this end, we use the fire simulation, which are cosmological zoom-in simulations run with PSPH. And we have of order 32 simulations at very high spatial and mass resolution. I will skip the detailed model of the fire simulation, but keep in mind, the fire simulation can explicitly resolve the launch and propagation of galactic wind on small scales. This is an example of the galaxy at redshift 2. These galaxies with This is the velocity curve. It has a very remarkable rotation disk. And this is the metallicity map of that galaxy. It has very significant negative metallicity gradient. However, this is another example in the suite. Also, a galaxy at redshift 2. This is basically a chaotic system with no evidence of rotation. This is basically it's a perturbed system. This is the metallicity map of that galaxy, which has no metallicity gradient at all. So here is our prediction of metallicity gradient versus redshift. The black points are the simulations, and the other symbols with arrow bars are observations available at this moment. So we can see we reproduce the diversity of metallicity gradient at any redshift. And here is the first prediction we made. If we look at metallicity gradient versus the degree of rotational support, which we use circular velocity divided by velocity dispersion as measurement of this quantity, we can see there is basically no feature in this parameter space. First, the strong metallicity gradients are more likely to appear in galaxies with a rotating disk. Second, these perturbed galaxies tend to have flat metallicity gradient. The two combined, I mean there is no galaxies located at this parameter space, basically. However, not all of these galaxies are mergers. Although they're perturbed galaxies, but merger are not the only mechanism can perturb these galaxies. So what else we can do to perturb a galaxy is the feedback. So we do a case study on a galaxy at redshift 0. It's a Milky Way mass disk galaxy at redshift 0. And the redshift 0 metallicity map is something look like that. It's very strong negative metallicity gradient, just like the observed galaxies in the local universe. So this is the time evolution of metallicity gradient. The x-axis is the cosmic time. The black line here is just the metallicity gradient. And the red line here and the blue line here are just the star formation rate and outflow rate within 10 kiloparsecs, just for reference. So we can see the galaxy has a transition time roughly around redshift 0.7. Before that time, the star formation is bursty and there are bursts of outflows. At lower redshift, the star formation becomes stable and there's no that strong outflows at all. So the metallicity gradient, on the other hand, during the bursty phase, the metallicity gradient is also bursty. It's not bursty, but have very huge time fluctuations. But during the stable phase of galaxy evolution, the metallicity gradient is basically a constant. So we focus on this time period when the galaxy is bursty. We just focus on one burst cycle and look at the example images of this galaxy. We pick 4 epochs to illustrate this one burst. First, the gas flows in and forming a disk. And then stars form in the disk, and it can quickly build up a negative metallicity gradient. Next, feedback from star formation can disrupt the galaxy, mixing the metal inside the SM and produce a flat metallicity gradient here. Basically, you can see all the strong outflow. The time where you have strong outflow corresponds to the flat of metallicity gradient. You can see a few examples here. And then the gas falls back, reforming a disk, and the next episode starts. So if we look at the individual snapshots during this bursty period and do the same exercise, plotting the metallicity gradient versus the degree of rotational support, the blue circles here are individual snapshots from here, and the gray points are from a previous plot that shows the whole fire sample. you can see pretty remarkably they are statistically identical. And bear in mind, although this is only a case study on one galaxy and on one simulation, at higher redshifts, the fire simulations shows that the burstiness of star formation is common at high redshift galaxies. And also the feedback is very efficient driving galactic outflows at high redshift than at lower redshift. So this is our prediction of metallicity gradient versus stellar mass and metallicity gradient versus specific star formation rate. There's a weak trend here, and probably because the feedback is very efficient in dwarf galaxies and in galaxies with high specific star formation rate. To summarize, we show the high redshift galaxies have diverse kinematic properties and metallicity gradients. Also, the negative metallicity gradient tend to occur in rotationally support galaxies which have a rotating disk. Perturbed galaxies have flat metallicity gradients, and bursty star formation and feedback can produce this diversity, although burstiness is not the only mechanism to produce the diversity. So we have a few open questions. I believe for questions.
Questions?
So this is really interesting. So in our group in Michigan, Sarah Loebman is there, and so she's thinking a lot about the stellar metallicity gradient and how the stellar metallicity gradient comes into being, and then how that evolves with time through the radial migration of stars, because radial migration of stars is very important in reorganizing the positions of the stars from their birth positions. So what I'm trying to, so I guess, what are or how are you thinking about trying to connect with the archaeological evidence that we have now from apogee and will have better from apogee plus Gaia in the next few years in terms of interpreting because this I guess makes pretty clear predictions about at certain ages you should just expect to see no gradient, right? Because there's nothing to rearrange through radial migration, etc. Right. Have you thought about how to connect that with the archaeological evidence?
Actually, you're right. In this galaxy, we actually have another study on the same galaxy I used for the case study here, which basically showed no metallicity gradient at higher redshift. And then when the disk starts to form, and there's a constant metallicity gradient. So for the stars, especially for the stars, what we see from that galaxy is radial migration is not that important in the later stage evolution. We see migration, but the metallicity profile does not affect very much by migration. Yeah.
Okay, let's thank Xiangcheng again.